Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello there, hello. Okay, this is lesson 5, scale factors. I think we're getting away from doing all these constructions and this should go a little bit quicker now. Let's see, classwork opening exercise, quick write, describe how a figure is transformed under a dilation with a scale factor equal to 1. So the first thing we're going to do is explain that. What happens if we have a scale factor that's equal to 1? Well, here's what it is. A dilation with a scale factor of r equals 1 produces an image that is congruent to the original figure. Same size. Okay, so now what happens if we have a scale factor where r is greater than 1? Okay, if r is greater than 1, a dilation with a scale factor of r greater than 1 will produce an image that is larger in size than the original, but the angles of the figure are unchanged, and the lengths of the larger figure are proportional with the original figure. Okay, so they're proportional and angles are congruent. So then what happens if we dilate fractions like 1/2, 1/4, 1/3, 2/3, anything between 0 and 1? Well, if that happens, then we get a dilation with a scale factor between 0 and 1 will produce an image that is smaller in size than the original, but the angles of the figure are unchanged, and the lengths of the smaller figure are proportional with the original figure. Okay, so now we have this discussion. Dilation theorem. If a dilation with center 0 and a scale factor of r sends points p to p prime and q to q prime, then the length of p prime q prime equals some ratio scale factor times the length of pq. Furthermore, if r does not equal 1 and o, p, and q are vertices of a triangle, then line pq is parallel to p prime q prime. Okay, now consider the dilation theorem when O, P, and Q are the vertices of triangle OPQ. Since triangle P prime and Q prime come from a dilation with the scale factor of R and a center O, then we have OP prime over OP equals OQ prime over OQ, which equals R, our scale factor, which we've done in prior lessons. There are two cases that arise. Recall what you wrote in your quick write. We must consider the case where r is greater than 1 and when r is between 0 and 1. Let's begin with the latter. Okay, before moving on, I wanted to bring in the diagram that would go with this statement that we just read. Okay, so if we have the point dilation centered at point O, which is right here, here's O, and a scale factor of r sends point P to P prime, so that sent it out to here, and Q to Q prime, then the length of P prime Q prime equals some scale factor of PQ, and they're parallel. That's what we were just saying right here. Okay, so if PQ was 5 and P prime Q prime ends up being 7.5, then we would take O P prime over OP equals OQ prime over OQ. Okay, so we went from 5 to 7.5. Well, that's a 2 to 3 scale factor, or 3 over 2. So R in this case would be 3 over 2. Okay. So there's the example for that. Okay, page 2 brings us to the proof that we're trying to do from page 1 right here. Okay, so statement, reason, and explanations. 1, a dilation with center 0 and a scale factor r sends point P to P prime and Q to Q prime. That was given. Okay, then we say these ratios are all equal. OP prime over OP equals OQ prime to OQ, which equals R, our scale factor. That is, okay, so the reason for that is, by definition of dilation, corresponding lengths are proportional, and the ratio of the corresponding lengths are equal to the scale factor of R being between 0 and 1. Okay, so now it says line PQ is parallel to P prime Q prime. So here's P prime Q prime, P is, yeah, say that 3 times fast. PQ is parallel to P prime Q prime. All right, so that's right here. Okay. So these are parallel. Let me just make that blue. How about I just do this? Okay. Now 3 says, okay, we just marked that. So why is that? And we can say by the triangle side splitter theorem. Okay, side splitter theorem. Number 4, a dilation with the center P. A dilation with the center P. So now we're going to dilate from P right here. And a scale factor P prime over P O sends point O to P prime from here to here. And point Q to R, which is here. Draw P prime R. So they drew this for us. So let's go over this again. Now our dilation center is going to be P. And we're going to take P prime, which is here, over the whole side PO. And that would make point O P prime. So we're dilating, it's less, R is less than 1. We're shrinking the big triangle down to this little one here. And in doing so, Q will move to R. So we're shrinking down OP, OQ. OQ is going to become P prime R. And they are going to be parallel as well. So by the triangle side splitter theorem again. Okay, that was wrong. So I caught that. And it is by definition of dilation, not by the triangle side splitter theorem second time. Okay, that is the definition of dilation. And then finally, number 5, we're saying P prime R is parallel to O Q. So it's marked here and here. Reason? Definition of parallelogram. Okay, we're continuing the proof on page 3. We're on step number 6. So now it says R, P prime, Q prime, Q is a parallelogram. This right here is a parallelogram. Reason? By definition of parallelogram. What is the definition of a parallelogram? A 4-sided figure with opposite sides parallel and congruent. So there's our parallelogram. Okay, so moving on, now we can say RQ over PQ. So this piece here over the whole thing equals P prime O over PO. And that's just the definition of sides or opposite sides of parallelograms are equal in length. Oh, I skipped one. RQ equals P prime Q prime. So we have RQ equal P prime Q prime, which I said earlier, they're also congruent. So now I can say and mark your diagram. RQ, this piece right here, is congruent to this piece right here, PQ prime, P prime, Q prime. They are congruent. Okay. Then we go to RQ. Where's RQ? RQ is this side here, is to PQ. So this small piece to the whole side is proportional to P prime O, P O. So this short side to the whole side. Reason? And that's by the triangle side splitter theorem. P prime R splits the sides of triangle POQ proportionally. Okay, so now we have RQ over PQ. Where's RQ? RQ over PQ. So it's this piece here. RQ is to PQ equals our proportional, our ratio, our scale factor. Okay, reason? By substitution, line 2. Okay, so I brought in that from line 2, the prior page, which said OP prime is to OP. OP prime is the whole thing, as OQ prime is to OQ equals R. So since one side of the smaller is proportional to the larger, then it works for all sides. And that's why we're substituting in from line 2. So what is being substituted? We have stuff equal to R. RQ is this short side. OP prime was this short side. So we replaced a short side RQ with OP, and then we replaced PQ. PQ is a whole piece with OP, which is the whole piece. Okay, so that's where the substitution from line 2 came from. And now we have RQ. So let me get rid of these marks. So now we have RQ. RQ is right here, equals the scale factor times PQ. Okay, RQ equals, so all we're doing here is multiplying this line up here by PQ on both sides, just a little bit of algebra. So if I multiply a fraction by its denominator, so if I put PQ here, just for a refresher, if I multiply this side and this side by PQ, let me do that again. Okay, if I put PQ here, and I put a PQ over here, then think of that as over 1, and the PQs cancel, and we get RQ equals R times PQ. Just a simple multiplication of an equation. So multiplicative property of multiplication, or yeah, equality. Multiplication property of equality. There it is. Okay, and now we have P prime Q prime. Where's P prime Q prime? P prime Q prime is this side here, equals the ratio times PQ. And the reason? Substitution of line 7. So here's line 7 here. We had RQ equals P prime Q prime, but RQ is R times PQ. Okay, so let me do some color coding here. R times PQ is here. R times PQ is here. Okay, but up here we have RQ equal to P prime Q prime. P prime Q prime, so that's substitution. So I'm setting R times PQ equal to P prime Q prime because it's equal to RQ. Okay, that's substitution line 11. So what were we trying to prove in the first place? So we have OP prime over OP equals OQ prime over OQ, which equals R. And then we have P prime Q prime equals R times PQ. By substitution, line 7. And is that it? Yes, that is the end. We proved that each piece is a scale factor of the original. Okay, page 4 brings us to an exercise. Try this on your own, pause the video, see if you can do it, and then we'll take a look at it. So here we go. It says prove case 2. If OP and Q are vertices of a triangle, O, P, and Q, it's this small triangle, and R is greater than 1, show that A, line PQ, is parallel to P prime Q prime, and B, P prime Q prime equals R times PQ. Okay, so the first thing we're going to do is, if R is greater than 1, line PQ proportionally splits the sides of OP prime and OQ prime of triangle OP prime Q prime. So all that's saying is, if we have a ratio greater than 1, then this side got split. This side splits. It's a side splitter. OP prime and OQ prime got split proportionally. So OP is to OP prime as OQ is to OQ prime. Okay. Continuing, by the triangle side splitter theorem, P prime Q prime is parallel to PQ, which is marked in the diagram. So next we construct a line segment PR that is parallel and splits the sides of O, P prime, Q prime, and it's parallel to OQ prime, as I said. So PR splits OP prime and Q prime, P prime proportionally, and PR is parallel to QQ prime. By the triangle side splitter theorem, side PR splits the sides proportionally, so P prime Q prime is to R Q prime as O P prime is to O P, and they equal the proportion scale factor of R. Now RQ prime, this piece of the parallelogram that stops at R, equals PQ. Because the lengths of opposite sides of a parallelogram, R, P, Q, Q prime, are equal. So P prime, Q prime is to PQ equals R. Or P prime, Q prime over PQ is equal to the R scale factor, and the length of P prime, Q prime equals that scale factor times the length of PQ. Okay. Okay, number 2 says to produce a scale drawing of triangle LMN using either the ratio or parallel method with point M as the center and scale factor of 3:2. Okay, so first thing I'm going to do is underline this. R equals 3/2. Okay, that's greater than 1. So we are going to make, this is going to be, the one we draw is going to be larger than this one. So if I just choose a point anywhere out in space, like right here, and call it O, and then I do my raise from O through M, from O through L, and from O through N, like that, and then get a ruler. Go to the top of the page and get it. Bring my ruler down, rotate it, and put 0 right on that line. Right on that point, I mean. So I want 0 right there. I'm going to measure ON, and I'm going to say that the length of ON equals 3.5 centimeters. Okay, I want to scale that by a factor of 3 to 2, so I want it bigger. So I'm going to multiply 3.5 times 3 and then divide by 2, or simply multiply by 3 over 2. So 3.5 parentheses 3 over 2 equals 5 1/4. So ON prime will equal 5.25 cm. Disregard that. I was going to do a fraction and I stopped. 5.25 is 5.25 is right here. So rotate this. That is N prime right here. I'm then going to rotate this over to my line OL. Measure from 0 to L, and it's 6. So OL equals 6. So OL prime equals 6 times 3 halves. That's easy because it's an integer. 6 times 3 is 18, divided by 2 is 9. So that has to be length 9. So I come out to 9 and put a dot right there. And that is going to be the point L prime. And then N, or OM equals 4.56. Let's just say 4.5 cm. This was centimeters as well. 4.5 centimeters times 3 halves. 4.5 times 3 halves equals 6.75. So OM prime equals 6.75 cm. 6.567 and a little bit more just in between those two. Move my ruler out of the way. That is M prime. And then I would use my ruler to connect the dots. Let me put my ruler on M, rotate it to N, and we'll make it green. So there is segment M prime, N prime. This one might not let me because it's snapping. So I have to use my straight segment command. And we're doing this in green. So that's from N to L. It's snapping as well. That's the best I can do right there. And then one from here to here. So there is triangle M prime, L prime, N prime, L prime, M prime, N prime, which is 3 halves LMN. Okay, page 5 brings us to part B, and it says use the dilation theorem to predict the length of L prime, N prime, and then measure its length directly using a ruler. And that got me thinking, I didn't do this correctly because I didn't read. Point M has to be our center. I created a point O, so I need to do this again. So obviously these values should all be the same. So if I take ON, well, there is no ON, so no, they're not the same. I take that back. Let's get rid of all of this. And we want to measure ML. Measure ML. The length of ML equals the length of MN equals, and the length of LN equals. So I'm going to measure those three. And that from L to M is 1.6, looks like 1.6, 1.7, 1.7. I'll say 1.7 centimeters. Rotate this around to N. And it is about 7. So I'll say LN is 7 centimeters. My ruler snapping to parallel or horizontal, I mean. And then I put M, I put my 0 right on M and measure ON, which is 6, or MN. MN is 6 centimeters. Okay, so ML prime is 3 halves of 1.7. So 1.73 divided by 2 equals 2.5 roughly. So I'll just say 2.5 or 2.6 because it was 2.55, in between 2.5 and 2.6 centimeters. MN has to equal 6 times 3 is 18, divided by 2 is 9 cm. And LN has to equal 7 times 3 is 21, divided by 2 is 10.5 cm. So I take my ruler, and I'm just going to do it this way with the ruler. I'm just going to put the ruler at 0 on M, put 0 on M, and ML was 1.7, and now I have to go to 2.6, 2.5, 2.6, which is about there. So there is L prime. Rotate this around to MN, and that was 6. And now MN prime has to be 9, which is here. And then finally, we just connect these. So let's do it in green. So there is, I can't quite do it because it's snapping, but it should go to that point. This should extend up to M, and then this should expand or extend, I mean, down to here. So there is L. The struggles are real, guys. L prime, and this is N prime. Okay, so this is what our diagram should look like. And obviously this has to be moved down a little bit, but as you could see, it was snapping. So now we can answer part B. It says use the dilation theorem to predict the length of L prime N prime. So now if I go back, L prime N prime is going to be, actually there should be a prime there. L prime N prime is approximately 10.5 centimeters. Okay, and we did measure directly using the ruler. Does the dilation theorem appear to hold true? And let's bring in the answers to this problem. Okay, so we would say the length of the line segment can vary due to copy production. Of course, by the dilation theorem, it should be predicted that L prime N prime is 3 halves Ln, and this is confirmed using the direct measurement. And then for the next one, we would say The dilation theorem does hold true. Okay, number 3. Produce a scale drawing of this triangle with point X as the center and a scale factor of 1/4. Now keep in mind that 1/4 is less than 1, so it's going to be a smaller triangle inside this triangle. So it says to use the dilation theorem to predict length of y prime z prime and measure its length directly using a ruler. Okay, so I'm going to get my ruler again. Go to the top of the page and get it. And I'm going to rotate it, measure the length. Actually, let me make since X is my center, I'll put 0 at X. Like so. And that is 4. So I'm going to label this as I go. XY, the length of XY equals 4 centimeters. Well, 4 centimeters times 1/4 or divided by 4 is 1. So XY prime should equal 1 cm, which is right here. I'm then going to rotate XZ. XZ is, let me just move it a little bit, 6.7. Okay. XZ equals 6.7 centimeters. And so if I take 6.7 and divide it by 4, that's going to give me 1.675. So XZ prime equals 1.7 centimeters approximately. 1.6, a little bit more right there. Let me use red right there. So we're done. And now all we need to do is connect those 2 dots. And there is Z prime and Y prime. So there's triangle X, Y prime, Z prime, 1/4 the size of the original triangle. And then we need to confirm the length of Y prime, Z prime and measure it directly using a ruler. And does the dilation theorem appear to hold true? So I measure this, try to be accurate, and that is 1.8. So now I'm going to answer this question. Y prime Z prime equals 1.8 centimeters. So the way to check that is measuring YZ, and it should be 4 times greater. So 1.8 times 4, 8 times 4 is 32, carry the 3. 4 plus 3 is 7.2 centimeters, if that is true. So I bring this up, put 0 right here, rotate it, and it's right around 7. We're off by 0.2 of a centimeter, and that's very easy to do when you're using a computer program, but it looks like it is about 4 times the size. Right, page 6 brings us to exercise 4. So pause the video, see if you can do this, and then we'll check it. So it says, given the diagram below, so it's a triangle and then a dilated triangle. It says determine if triangle DEF is a scale drawing of DGH and explain why or why not. Okay, so here's what we would do in this problem. So you take the whole piece. Now, EG is 3.75 and DE is 3.2. So DG equals DE plus EG. Agreed? And sometimes students forget to do this. So I need to find the whole length DG. So DG equals DE 3.2 plus 3.75. So DG equals 6.95 millimeters. Okay. So then you take apart, the small triangle, DE. So then you set up a proportion and check. So I'm going to do it over here. DE is to DG as EF, the small triangle given side, is to GH. And then we substitute in our values and they should come out to be the same if it's true. So DE is 3.2 divided by DG, which is 6.95. And that is supposed to equal EF, which is 5.9, divided by the whole side over here, GH, which is 11.9. Okay, get my calculator. Clear. 3.2 divided by 6.95 equals, and the answer came out to be 0.4672. I'll round out 4672. And then I'm going to do the same with 5.9 divided by 11.9. And if they are a scale drawing, then these values will be the same. So I take 5.9 divided by 11.9. And I got 4.958. And obviously 4.46, not 4.9, it's 0.4958. Try that again. Let me make sure my number's right. 0.49579 or rounds up to 8, so that's correct. And obviously 46 100ths does not equal 49 100ths. So now I will answer the question. So let me move my work here. Oh my. So that's what we concluded. So it said the answer is no. If triangle DEF was a scale drawing of the big triangle DGH, then DE over DG equals EF over GH, which I have just shown. And then they show their work. 3.2 over 6.95 equals about 4.46. Actually, it's 0.47. And EF 0.59 over 11.9 comes out to be approximately 0.5. The ratios of the corresponding sides are not equivalent, so the drawing is not a scale drawing. Page 7 brings us to the end of lesson 5. Go to your problem set.